All right, so in this video I want to at least introduce some of the thinking around problem number 3. Problem number 3 is a problem that I think involves a fair amount more thinking than the problem we did in the previous video, and that you really need to think carefully about what the conditions are that you might have to meet in the problem. It's also a problem that benefits enormously from your thinking hard about what the right way is to frame the problem when you start with, because the way that it's actually written has a lot of kind of stuff that's just not very helpful. And so taking a little time to step back and say what actually is important for me to find in this problem in order to actually get somewhere, I think makes your life a lot easier. So you're given a lot of dimensions in this problem, for example, and it's probably not the easiest way to think about things to use those dimensions when you're actually trying to solve the problem. So let's start with asking what the question is. So we've got this block, right? The block is attached to a cable, right? The cable goes up past some pulley to a second pulley, and that second sort of wheel is attached to a motor, right? And that motor is applying some kind of moment that's presumably actually in this direction, right? That's trying to pull in that cable, right? So we're trying to wind up this cable, and in winding up this cable, there are a couple of things that might happen, right? You can certainly imagine that one thing might happen is that this thing might slide, right? Another thing that might happen is it might actually get lifted off the ground, depending on what the location of this is. And another thing that might happen is it might actually tip. Right? So there are a lot of possible things that could happen here, and you're asked to sort of think about and figure out which of those things happen under which conditions. Right? So what's our approach going to be for this? Well, the approach for this initially will be pretty similar to what we did last time. We're going to look at the thing that we're interested in understanding the sort of behavior of, and draw a free body diagram for that, and then think about how do we mathematically express the conditions of equilibrium given that free body diagram. So I'm going to cut this box out of the rest of the universe, right? I'm not going to worry about this pulley, I'm not going to worry about this motor, because really the thing I'm interested in is what is happening to the box. In order to think about what's happening to the box, the only things that the box interacts with are this cable and gravity and the sort of contact force between the ground and the box. So let's first take the step of drawing the free body diagram for this thing. And this free body diagram will be a little bit more interesting to think about because of the fact that we have some forces where we actually don't know exactly where they're going to act. So there's my box. Obviously, one force I know all about, right, is the gravitational force that will act at the center of mass of the box, right? A second force that I actually know a fair amount about is the tension in the cable, right? There's some tension in the cable. And at this point, I'm going to just use this opportunity to introduce a direction that will be helpful to me. I'm going to introduce the direction r hat, or let's just use r hat for that, which is the unit vector that points along that cable, right? And we could think about that r hat as being made up of, if this were at an angle of theta, I could write it out in terms of I hat and j hats, right? You've seen that in the previous video, so we're going to use that same idea again here. Okay. Now, obviously, those aren't the only forces that are involved, because this box has a contact force with the ground. And if it's not moving, that contact force actually there could be two things going on. One is there's going to be some distribution of normal forces along this surface, right? And so somewhere along this surface, there will be a normal force up, right? And there will also be some frictional force acting, right? And we actually don't know necessarily where that normal force acts. In fact, where that normal force acts will depend on what forces I apply. So we're going to say that that normal force is acting at some distance d away from where the center of the block is. Okay. Now I've drawn it to the left. Why have I drawn it to the left? Well, I've drawn it to the left because initially, if I think about pulling on this, when there's no tension on this, the normal force would be directly underneath the gravitational force in order to give me zero moment, right? When I do start to apply a tension to it, I've now got a moment that's wanting to rotate the object in this way, I need the normal force to oppose that moment. So that's why I'm assuming that the contact point is going to be over to the left instead over to the right. But that's an assumption I'm making, and certainly I could end up finding out d was negative if I somehow was wrong in that assumption. Okay, so there are all of my stuff in the free body diagram. What do we know and what do we not know? Well, I propose that t is something where we're just going to assume a value, right? Because what we're after here is we're trying to figure out for what value of t are certain things true, right? So we're going to basically assume some t and then see what happens when that t is assumed, okay? The normal force, right, is a constraint force. It's whatever it has to be. Such that the block does not sink into the ground, right? So the normal force has to be such that the sum of forces in the y direction has to be greater than or equal to 0, right? And notice that the normal force actually is not allowed to be anything other than positive. And the reason it has to be positive is that the ground doesn't actually suck down, well, the gravity sucks down the block, but the normal force actually is resisting the block getting pushed into the ground. If I pull up on this block, it's free to get lifted. So the normal force is a constrained force that must be positive, right? By the same token, this frictional force is also a constraint force because it's static friction, right? If I'm assuming static, then that frictional force is whatever it needs to be so long as the magnitude of the frictional force is less than the coefficient for static friction times the normal force, okay? So I've actually got two forces that I sort of don't know what they are right now, right? One is how big this normal force is, and then the second is, even if I do know the normal force, all that tells me is how big the frictional force can be, okay? So we have some stuff we're going to have to figure out in this problem. All right, so now that we've got the free body diagram, our next step in dealing with this is going to be to translate that free body diagram into sort of a mathematical statement. If only I could spell statement of equilibrium. Well, the mathematical statement of equilibrium in general, of course, is sum of forces is 0 and sum of moments is 0. Let's start by saying the sum of forces is 0, right? If I look at that, that says that t times r hat, right, this force, minus mg times j hat, plus the normal force in the j hat direction, plus the frictional force, whatever that is, in the I hat direction, that all has to be equal to 0, right? That's one condition, okay? And if I just take a second to think about that, right, I can see a couple of things. One is that I can collect terms here and determine, for example, that t times, if I call this theta, so t times sine of theta plus n minus mg has to be 0, right? That's the j hat component of this vector equation, right? The upward force from the tension plus the upward force from the normal force minus mg has to be equal to 0 in order for it not to get lifted off the ground, right? And some of the I hat component tells me that the frictional force, or minus t times cosine of theta, right, because my I hat component of r hat will be minus cosine theta, plus the frictional force also has to be 0, right? So in order for me to be not moving in the x direction, I need the net force in the x direction to be 0, so that means that my frictional force has to be equal to and opposite the tension force times cos of theta, okay? So we could take this a little bit further and ask the question, okay, well, what does that mean is allowed in terms of what the tension is? Well, if we think about what's allowed, there are two sort of constraints that we have to meet. One is that the frictional force has to be less than mu sub s times n, right? So I can actually say that the largest value of the tension is going to be tension times cosine theta is equal to mu sub s times n, right? That's the point at which this frictional force has reached its static limit, right? And so that sort of corresponds to the condition where, say, theta is 0, right? If I'm pulling at horizontally, right, I'm going to start to actually accelerate the block horizontally as soon as t times 1 cosine of theta is equal to mu sub s times n. Okay? But it's also, but notice that the normal force in turn depends back on the tension force. So I've actually got two equations and two unknowns in this, right? So I need to actually figure out not only what the frictional force is, but also what the normal force is in terms of what the tension is. And so I can go ahead and solve that. So let's see. Let's do that. So if I actually plug this in for normal force up above, right, I'm going to get t times sine of theta plus mu sub s times, 1 over mu sub s times t times cos of theta, right, has to be equal to mg. Okay. So if we sort of look at that and we pursue that a little bit further, what we find is now that t is equal to mg divided by sine theta plus 1 on mu sub s cos theta. So what does that mean? That this is the t for which we break the frictional constraint. Okay. And if you look at that, it's an interesting expression, right? So first of all, when you set theta is equal to 0, right, when I'm pulling horizontally, this says that my tension then is simply mg divided by 1 over mu s, or in other words, my tension is mu s times mg, right? That makes sense. That's the normal force for a block just sitting on the ground times mu s. That is sensible. As I increase the angle, there are a couple of things that are happening, right? One of the things that's happening as I increase the angle is that I'm actually reducing the amount of force in the x direction, right? Because I've got more and more of my tension pulling up. But the other thing that's happening is I'm actually reducing the normal force, right? Because as I start to pull up, the normal force gets smaller and smaller. And so there's actually potentially interesting behavior here where the tension is not necessarily monotonically dependent on theta, and we'd have to do a little bit of thinking about how that depends on what mu s is. Okay? So that's one of our equilibrium conditions, is that the sum of forces is equal to 0. But that's only one of the equilibrium conditions. There's a second equilibrium condition, right, which is that the sum of moments has to be equal to 0, right? So let's look at the diagram and think about that for a second. So here's my block. I've got a tension force that's pointing in some r hat direction, and I've got a gravitational force that's pulling down. And I've finally got a normal force and a frictional force that are acting someplace along this face. Well, what's the best possible case? As I pull harder and harder, as I said, the normal force is going to move over as far as it can until actually it gets to the edge here, right? And it's when the normal force gets to the edge that we're at the tip condition, right? So we're at the tip condition when the normal force is pointing up here, frictional force is pointing to the right, and the location that those forces are, those equivalent forces are being applied is at the corner, okay? So we're going to think about that condition for calculating what the sum of moments are. Right? And what I'll do is I'll choose to put my origin at the location where the unknown forces are, because that will actually allow me to calculate what the moments are much more easily. Right? So, okay, I've chosen my origin to be there. Let's call this position A vector and this position B vector. Right? So A vector goes from the center to where the center of mass is. B goes from the corner, A goes from the corner to the center of mass. B goes from the corner to the connection point, right? So if I take my sum of moments, I'm first of all going to have a moment that will actually be a clockwise moment due to the gravitational force. So that will be a vector cross minus mg j hat. Right? That will be my first moment. And then I'll also have another moment that's due to the tension force, which will be b vector cross t times r hat. Okay? And that's got to give me 0. Well, let's think about that for a second just a little bit more explicitly. Like if this block is some width w, right, and some height h, what's a vector? Well, a vector is equal to w on 2 I hat plus h on 2 j hat, right? So this is w on 2 I hat plus h on 2 j hat quantity crossed with minus mg j hat, right? I hat cross j hat is k hat. J hat cross j hat is 0. And so this is going to give me minus mg w on 2 in the k hat direction, right? In other words, that will give me a clockwise moment. And the size of that moment depends on this distance, right? The moment arm, which is w on 2, and also depends on how big the gravitational force is. This, on the other hand, right, b vector is actually w on 2 I hat plus h j hat, right? And so this will give me w on 2 I hat plus h j hat crossed with minus cos theta I hat times crossed with t times minus cos theta I hat plus sine theta j hat. And so if I take this, I hat cross I hat 0, j hat cross j hat is 0, I'll get a w on 2 times t times sine theta. And that's I hat cross j hat, so that's positive. And then I'll also get an h times t times minus cos theta times j hat cross k hat. J hat cross I hat is minus k hat, so I'll get a plus h times t times cos theta, right, on the k hat direction. Okay. So now I've got this plus that, right, has to be equal to 0. Well, if I go ahead and solve that for t, right, I pull out my t, I'm going to get t is equal to plus mg w on 2 divided by w on 2 times sine of theta plus h times cos of theta. Okay. Now we can take a second to think about this expression as well. Notice that when w is a lot less than h, what happens? Well, this is small, h is large, and so the tension that I need to tip it over is quite small when w is quite a bit less than h, right? That corresponds to a block that's really narrow, right? If w is a lot greater than h, on the other hand, right, so this will be much larger than h, so this term is going to dominate this term, and so I simply get mg divided by the sine of theta, right, which basically says that in order to tip when the block is fat and short, right, if the block is fat and short, I basically need to be lifting up with a gravitational force, right, that the upwards component needs to be basically mg. So both of those also sort of make sense. So at this point we actually have two conditions on t, right? Right, we can either break, we can actually keep the frictional constraint, but break the constraint that the sum of moments is 0, right? And that's if we lift up enough, or if we lift enough if we rotate enough about this point with the tension force, or provide enough moment about that point with the tension force. That's one way that we can cause it to move. And the second way that we can cause it to move is if we provide enough tension force to actually break the frictional constraint. So I've now gone on for 20 minutes on this problem. I've not certainly answered the entire thing, but I hope that I've given you some of the building blocks and pieces that you need to successfully deal with this problem. Sorry that went on so long. Hope that's helpful.